Now, of course, when we study the physics, I mean, no matter whether we are studying physics or any other subject, we want our endeavor to have some impact on the society. We want to bring some good to this world, and that's the ultimate objective. That's what we are aiming for. And that is what the physics actually does. I mean, physics is one of the very few things which allows us to create a large impact on the society. So physics actually allows us to do that. So think about it this way. Now, we all know that steam engine was invented, and after the invention of the steam engine, it actually triggered, it started the entire industrial revolution. And once the industrial revolution started, there was no stopping. After that, we created big factories, and after that we have silicon chips and right. I mean, so there were several technological improvements, subsequent technological improvements after the steam engine was after the invention of steam engine, which impacted our society in a big way. After the second biggest revolution which happened was the invention of the computer chips. So the computer chips happened, and then we have computers which were able to compute things very fast. We were able to solve the problems, previously unsolvable problems. We were able to solve those. We were able to predict the weather, which of course involves a great deal of computation power. And then the next revolution happened when we were able to miniaturize that computer. So with the use of our phones, we are now able to do things which previously were unimaginable, even with the fastest computer. So all of those things have changed our society in a big way. And underlying all of those things, all of these inventions, is physics. Without physics, these inventions, these technological innovations would never have happened, and our society would not be the same, for better or worse, right? Our society has actually changed a lot because of these technological innovations. Now the next generation, the future, is of course the travel by rockets to various planets. We would be doing that, and when that happens, our society would again change, right? So we first we'll have to make some physics would have to make great contributions. We'll have to solve the unsolvable problems using physics, and once those problems of rocket travel are solved, then we will be able to launch rockets and go to the go to other planets in the same way, hopefully, as we go to school every day, right? So similar way we would be able to go to rockets and use rockets and go to other planets, hopefully. But that would only happen if physics is able to bring the answers to the unknown questions. And of course, when that happens, when the when the rocket travel becomes that much easy, it would be a big change to the society. I mean, we can't envision a society where people are living like of the same family. A few people are living on Earth, and the few people are living on Mars. So of course, that would be again a big change to the society. So think about it. The contributions that you make to physics would actually bring technological innovations which people have never thought, and would change the society forever, right? So that's the power of physics. So study it well, study it with interest, and of course that will help us all in living a better life. So this is an example of the technology, how it actually changed us. Everything that we see around us is now moved by technology, and of course underlying it was the physics. The wireless communication, it happened. So why did that happen? It happened because Hertz was able to do his experiments, and from there we know that electromagnetic waves were discovered, and then there were those famous 4 equations of Maxwell, and then came on the technology was built using those electromagnetic waves, and that is what we are using today in our cell phones, and that is now become an integral part of our life. It has just become an integral part of the society. Everything around in the society revolves around the technologies which once were the simple problems that physics was able to solve. Another important dimension, right? Another important such invention was the discovery of atomic fission. Right? Once we were able to come up with the answers to the questions of how atom was, there was nucleus, right? So the Rutherford Goldfield experiment and Bohr's atomic model based on that. Once we started understanding how the atom was, we were able to then break it. We were able to harness its power, and of course, it is one of the important sources of power for India and for some of the other countries like Japan. So those people now rely a lot on atomic power. Of course, technology has both the sides. So using this nuclear power, we not only were able to unfortunately create the nuclear power plants, but we were also able to create nuclear weapons, and that's unfortunately the nature of man. Okay, so but for better or for worse, the technology is there and it is available for us to use, and we can improve the life of millions of people, right? When they were finding out, when the Rutherford was doing his experiment, he didn't think that his technology, his experiments then would be using that. We would be able to create the, once we understand the atom better, we would be able to create nuclear fission. He didn't really know that, but that small experiment that he did changed the course of mankind forever, right? I mean, atom bombs also changed the course of mankind forever, and of course the nuclear fission, the clean energy, not so clean, but the energy that we get from them has of course changed our life. So similar thing would happen to you. You would make a small physical discovery and it would bring a large technological evolution, and that would completely change the world. And let's hope that each and every one of you is able to do that. Energy sources is very important, right? See, the key idea here is that human beings have insatiable need for energy. We need more and more energy to fulfill our endeavors. We are not happy with just walking around. We need cars now. We are not happy with cars either. We want airplanes, and even airplanes don't make us happy. Now we want rockets. Each of these endeavors, it takes more and more energy. And with this insatiable need for energy, we now need technologies which would be able to deliver the green energy required to fuel our ambitions. And that of course will be done by the future generations, your generations. You will be able to do all of those things. Now here are a few technological innovations, a few important people who did experiments, few important physicists who did some experiments, who did some discoveries, theoretical or experimental, and whose discoveries have actually changed the world in a big way. So Archimedes, how can we forget him? He is one of the most talked about physicists of all times. And Archimedes actually gave us the principle of buoyancy. How would the solids, when they are immersed in liquid, how would they behave? Whether they'll submerge, whether they'll float. We'll talk about all of those things. And of course, he came up with the principle of lever. He said with the lever we now understand that we can create. With the lever now we understand that we can even lift very heavy objects. Okay, that was the power. We can do even the most heavy lifting using the simple principles of the lever. And of course, that is also something that we will understand. Galileo gave the law of inertia. So remember that even before Newton, people understood what was inertia. So Newton, one of the laws of Newton is actually deals with the inertia itself, that the body at rest would remain at rest. That is the thing. But even before Newton, people understood that the body at rest would remain at rest until I do something to it. So that was the law of inertia. Then Huygens was there, and he gave the wave theory of light. So wave theory of light, now we understand by the later work of Maxwell and others, that we understand that light is not only waves, it is also particles. Okay, so that is an important contribution of Einstein, Maxwell, those people. Now we understand that it is not only wave but also particle. But first, people thought that light was a wave and only a wave, and using his theories, they were able to explain a lot of things. Using these basic wave fronts from the Huygens theory, we can understand the refraction of light. Those basic things we can even understand from the wave theory of light. Of course, Newton is very famous. We know his law of universal gravitation. We understand that with this law, if I throw this feather and this stone, they will both go down, and if there was no air drag, they will reach the earth simultaneously. See, with that Newton's law of motion, Newton's law of gravitation, universal law of gravitation, it not only sort of determines the motion of these two objects, when they fall down, it also determines the revolution of Earth around the sun. So it applies, it has application which goes from Earth to the space. So that's why it's known as universal law of gravitation, because it applies, its application is vast. Okay, so let's just throw this and see the law of gravitation. I'm not going to really throw the stone and break something here so that it will I mean, you might be saying that, oh sir, throw the stone, but I'm not going to do that. Then we have Newton's laws of motion. Those were also very important. And reflecting telescope. So with his invention of the reflecting telescope, they were able to observe the skies, and from there on came the lot of discoveries about how the universe actually works, how the celestial bodies, how do they work. Faraday's laws of electromagnetic induction, they are used everywhere. What they would say is that what would happen if I moved a coil inside a changing electric field. So what would happen? And those laws of induction actually explain a lot of devices that we see around us, like transformers, motors, generators. All of those things are important in our daily life. Then Maxwell's electromagnetic theory, we have heard about this quite a lot. We will study it a little bit, and it gives us equations which not only describe the electromagnetic waves, it also describes the light, right? So it encompasses everything. Electric field, magnetic field, and the light. It describes all of those three things. It unifies all of those three things, the Maxwell's 4 equations. So very, very important. Hertz was, of course, a very important experiment. With this, he created the electromagnetic waves, and that is what we use every single day. Then of course came Bose. Bose was very, very important, and he actually discovered the ultra short radio waves. So ultra short radio waves are the radio waves whose wavelengths are less than 10 meters, and the radio waves can be very, very they can be very, very long. They can go long wavelengths can be above 3000 meters. So the ultra short wavelengths are those wavelengths which are less than 10 meters, right? So that is what we will write here. Then came the Roentgen, who discovers the X-rays. So Roentgen was again very, very important. Thomson, he discovered the electron, and then he gave us the plum pudding model, the model which actually makes us all very, very hungry. And then we cannot really forget the Curie couple, very, very important. They discovered the several experiments on the radioactive elements. Einstein was important. He actually gave the explanation for the photoelectric effect and won the Nobel Prize. So photoelectric effect, what does it mean? It means that when I throw electrons on certain objects, they emit, when I throw photons on certain objects, they emit electrons. And that is very, very important, because it tells us about the quantized nature of the energy. So that is again important. Of course, he is more known now for his theory of relativity, which is also very, very important. It actually increased the dimensions in which we were able to put our theories, right? Put our theories to use. So Albert Einstein, we can never forget. Then there are more important inventions. So Hess actually discovered the cosmic radiation. So cosmic radiations are high energy radiations which enter the Earth's atmosphere from the cosmos, from the universe, right? So that's why they are known as cosmic radiations. High energy radiations, they consist of mainly protons and the nuclei of the atom. So the electrons are stripped out. The electrons are no longer there. That is how energetic these radiations are, that the electrons are just removed. Millikan was important. His experiment to measure the electronic charge, we will study that. Rutherford, we already know, there is a separate class on that. You should look at that nuclear model of an atom. So he was the first to actually prove that there is a very heavy center in each atom, and that is the nucleus of an atom. Bohr was built on this Rutherford's discovery, and then he came up with the quantum model of the atoms. C.V. Raman, we can never forget. He is one of our favorites, and he actually discovered the inelastic scattering of he studied the inelastic scattering of light by molecules. So when light hits the molecules, there are two kinds of scattering which could happen. One is inelastic, in which the energy is absorbed. So the energy of the reflected light is actually less or the scattered light is actually less than the energy of the incident light. So some energy is absorbed, and that is why it is known as inelastic. Elastic means that no energy is actually absorbed. Then Gogli is again very, very important because he gave us the wave nature of matter. So Borgley is, then there is this famous Borgley wavelength also is there, and that is the he told us that the matter has both. It can be a wave, and it can also be the basically it can also exist as a particle. So he actually worked on that. Saha was famous because he gave us the thermal ionization. So when I heat something, I can actually cause ionization in those particles, and that's what we see in the upper layers of atmosphere. We're able to see that. Bose actually worked on the quantum statistics. So what is quantum statistics? The thing is, when I have a single particle, then then it is easy. I only have to worry about that single particle. If I apply force to it, what would happen? Okay, so those are the kind of things that I can do with a single particle. When there are particles of a gas, for example, molecules of a gas or atoms of a gas in a closed container, then there are several thousands of particles. So how do I describe the behavior of each and every particle? It becomes very, very difficult. So in those cases, we are not really concerned about the behavior of a single particle. In those cases, we apply something known as classical statistics, right? So there are two things. Classical statistics. So that is the first thing, and using those we can understand the behavior of those group of particles all together. Of course, when those particles are far apart, then we apply the classical statistics. When those particles they come close together, then we apply the quantum statistics. So that is something that S.N. Bose actually worked on. And who decides whether the particles are far apart or whether they are close together? Now that was the work of the Borgley that we saw right here. Okay, so all of those things are related. If you think about it, those are the kind of things. It is not just one person who is doing it. It is the many people who contribute to a single discovery. It is every discovery that we make now, everything that we do now is built on the work. We are standing on the shoulders of these giants. Actually, you can think about it that way. Okay, so that is what we come here. Now the next thing is the Pauli. The Pauli gave us the exclusion principle. So exclusion principle tells us that much we have actually studied. It has much wider application, but on electrons we use it, right? The 4 quantum numbers of the electron cannot really be the same. That is what we say in case of electron. That is what the exclusion principle tells us, and that is we have used it already to fill the orbitals in various atoms. But it has much wider applications. It is not only applicable to the electrons, but it is applicable to many more particles. Then of course Fermi, he worked on the controlled nuclear fission. So nuclear fission can be controlled or it can be uncontrolled. Uncontrolled is what makes atomic bombs. If it's controlled, then we can harness its energy in the nuclear power plants. Heisenberg has the famous uncertainty principle, which tells us that we cannot measure, there are a few properties of small subatomic particles which cannot both be measured accurately, right? So there are these pairs of properties that we cannot if we measure one of them accurately, then the other would become inaccurate, right? That is the uncertainty that comes from the Heisenberg's uncertainty principle. Then we have the Dirac. We already talked about him in the earlier lecture. He worked on the quantum statistics. So like I said, we already know what quantum and the classical statistics, what those are. Now we come to cyclotron. Now cyclotron is very, very important because it's used in our modern day imaging devices, right? So if you go to a medical center, hopefully no one would have to visit a medical center, but if you go there for various your tests, then imaging devices are there, right? Like for example, there is MRI, CT scan. Those imaging devices are used. So in those imaging devices, some of those imaging devices, cyclotron is actually used to create the particles. So it's a compact device. It's a compact particle accelerator. You can say that, and it can create a variety of radio isotopes. Then we have Chadwick, who gave us the neutron. So very, very important. Without neutron, we would not really be able to understand the atom completely. Then Yukawa gave us the theory of nuclear forces. So we know that the nuclear force is there, the strong nuclear force is there, and Yukawa contributed a big deal about it. We'll learn about the strong nuclear force, the weak nuclear force a little bit later. Bhabha was a great Indian scientist. He actually studied the cascade process. So cosmic radiations, we already understand, they are very high energy radiations which enter the Earth's atmosphere. Now when they enter the Earth's atmosphere, they interact with the particles in the atmosphere and produce even more particles. Now those particles interact with more particles, and thus there is a cascade reaction. And who studied that? Bhabha studied that. Landau actually gave us the theory of the condensed matter. So when matter is condensed, for example, like liquid helium, right? He worked on those kind of things. How does it behave? Chandrasekhar, again a very, very important. Chandrasekhar gave us the Chandrasekhar limit. Now what is Chandrasekhar limit? Now we know that stars, they can end their lives two ways. Either they can become a white dwarf or they can become a neutron star. So which star would become what is given by the Chandrasekhar limit, and that was the very, very important contribution. Now Bardeen actually gave us the worked on the transistors and also the theory of superconductivity. Superconductivity is again very, very promising theory. What it tells us is that if if something is superconductive, right? For example, there is this coil. If I pass electricity to it, then it will resist the flow of the electrons. But if it were superconductive, then it would offer no resistance, and my electrons would just flow through without any loss in energy. So you can see that it's a very powerful concept. Now, transistors we use in everyday life. It is just there in all electronic devices. They are just a switch. Okay. Now Towns gave us the maser and the laser. So laser is the light amplification by stimulated emission of radiation. So light amplification. So we are doing the amplification of light. Okay. So it is very simple. And how are we doing it? We are doing it by stimulating. Stimulating what? We are stimulating the atoms. Stimulating the electrons within the atom. So when electron is stimulated, it rises to higher energy level. When it comes down, it emits certain frequencies, and it is that frequency of those that emitted light that results in laser. So it's light amplification. We are increasing the amount of light. How are we increasing it? By stimulating emission of radiation, by stimulating the electrons, which are then subsequently will release even more light. Maser is similar, but instead of light we have microwave. So it's microwave. Okay, so microwave amplification by stimulated emission of radiation. Then Salam, he actually worked on the unification of weak and electromagnetic. See, one of the most important endeavors of physicists, right? We already saw this. Physicists, one of the most important endeavors of physics is actually to unify everything. We want to boil everything down to a single law, hopefully, that is applicable everywhere. And one of the things here is that the Salam did was he unified the weak and the electromagnetic force. So there is weak nuclear force, we'll study that later on, and then there is electromagnetic force which happens between the charged particles. So those two things he was able to unify. Only under certain conditions he was able to say that when the Big Bang happened, the temperatures were very high, and in that time the two forces were actually just one. But even in that limited period, if the two forces were one, it gives us a lot of insight. It gives us a lot of confidence that perhaps we can unify even more forces. We can just treat them to be one, and that is actually a good thing. Then we come down to in this section we come down to some of the main discoveries which have happened. So here are the discoveries. Here are the technologies that we use, and what is the area of study that gave rise to that technology, right? So this is the area of study. For example, laws of thermodynamics allow us to build better steam engines. So laws of thermodynamics are actually useful in steam engines, not only in steam engines, but any kind of engine, in any kind of refrigeration, your air conditioner, your refrigerator at your home. Then controlled nuclear fission, the study of controlled nuclear fission helped us build nuclear reactor. Similarly, how do we generate the electromagnetic waves? That helped us develop the radio and television. Digital logic. So what is digital logic? It is the logic of ones and zeros, right? So that is the digital logic, and that helped us build the computers. Similarly, we already talked about the lasers. superconductivity, right? So with the help of superconductivity, we can produce high magnetic fields. Now, how do we produce magnetic fields? Typically, we don't have such a strong magnet. So how do we do that? We produce magnetic field by moving the electrons. Whenever the electrons, charged particles, they move, they produce magnetic field. So when I move the electrons, I produce the magnetic field. To produce a strong magnetic field, I have to move large amount of electrons. When I move large amount of electrons, then there will be a lot of resistance, right? Then the wire would oppose their flow, and then I would be in trouble because that would generate a lot of heat, and that creates its own set of problems. So with the help of superconductivity, if that heat, if that resistance of the wire is eliminated, that heat is eliminated, then I can theoretically just pass an infinite amount of current inside this small coil and produce very large magnetic fields. And of course, these magnetic fields are used, they have medical applications, we know that. And these magnetic fields are also again in imaging devices, right? MRI, for example. So these magnetic fields have used there, and these magnetic fields have also have uses in the colliders, right? So particle accelerators. So those that is where also they come into play. Newton's laws of motion, they are helped us make rockets, right? Third law of motion, we cannot forget that. Of course, we already studied the Faraday. We already sort of talked about the Faraday's laws of induction. Then when we look at the conversion of the energies, how the energies are converted, it helps us make the power from hydroelectricity or from thermal power plants, right? Then particle accelerators are very, very important because they actually helps us. They are at the cusp of the scientific discoveries. So particle accelerators, they are used by the physicists to discover new particles, which in turn gives rise to new kind of physics. And those particle accelerators are based on our understanding of charged particles in electromagnetic fields. How do they behave? Because particular accelerators, as the name suggests, would accelerate the particles. And how is that acceleration done? That acceleration is done by using subjecting the particles to high magnetic and electric fields. Then sonar, the application is sonar, right, which is used by all the ships, which is used by the submarines. And how does it, what helped us make sonars? Understanding of our reflection of ultrasonic waves. Once we understood that, we know that BAT uses it, and of course now we use it as sonars. Once we understood the total internal reflection of light, we will study that further. But under certain conditions, the light, instead of getting refracted from when it travels from one medium to another, instead of being refracted, it gets reflected. And that application, that is known as total internal reflection. And of course, this total internal reflection is used in optical fibers. When we understood thin film optical interference. So what is thin film optical interference? When I have very thin film, let's say thin film of oil on the surface of a road, the thin film of oil, what I can do is that there will be two rays of light. One ray of light which will go down and come back reflected from the road itself, from the base surface, and right, that will be one ray of light. The second ray of light would actually hit the film and then come back up. So those are the two rays of light. I can create films in such a way that those two rays of light cancel each other out, and in this way there is no net reflection. So that application is right here. Once we understood the wave nature of electrons, right, how can we forget the Young's double slit experiment? So that is again very, very important. Once we understood that the electrons are not only particles, they are also waves, then we were able to develop the electron microscope. Einstein's photoelectric effect helped us build the photocells. Photocells means that it is something that we use every day. As soon as there is, for example, in the street lights, they use photocells. As soon as there is daylight is there is a photocell there which detects that, oh, there is daylight here. Now let me turn off the street light, and the street light would automatically be turned off. Similarly, it will be turned on automatically in the evenings. Then tomahawk. See, tomahawk is a machine which is able to confine a state plasma, right? So plasma is a state of matter. So plasma is a very, very sort of hot state of matter. We find plasma in the ionosphere. There is plasma. So it is a state of matter where the electrons are gone, right? They are no longer tied to the respective nucleus. So in this kind of state where we have the electrons, where we cannot distinguish between the various atoms, how do we contain such a state, right? So this kind of state happens at very high temperatures, which are used in fusion test reactors. And tokamak is the machine which is able to do this, confine this plasma using magnetic and electric fields. Then meter wave radio telescope, giant meter wave telescope, it is there in Pune, and it helps us understand more about the cosmic radio waves. So we know that there are radio waves which originate from the cosmos, and with the detection and understanding of this cosmic radio waves, we are able to understand more about the universe. And this telescope is in India. It's in Pune. Bose-Einstein condensate. With the help of Bose-Einstein condensate, how was Bose able to develop this condensate? How was he able to do that? By cooling the atoms, right? So Bose-Einstein condensate is a completely different state of matter. Just like plasma is there, similarly, this is a new state of matter. And this state of matter has its own kind of application. It is useful in certain circumstances. Okay, so for example, Bose-Einstein condensate is very useful in quantum physics. So if I'm developing a quantum computer, I need to understand how Bose-Einstein condensate can be developed, and how I need to study how it behaves. So in quantum study, this is very useful. And how was Bose able to develop this condensate? He was able to develop the condensate by understanding, or by trapping the atoms by using laser and magnetic field. So with magnetic field and laser, we are able to trap the atoms, and we are able to cool those atoms down to very low temperature. And once we do that, then we are able to produce the Bose-Einstein condensate, and it is very important in the quantum study. So all of these are the technologies. Okay, these are various technologies that we have, and these are the sciences, these are the basic physics which enables us to develop that technology. So hopefully with this you appreciate the role of physics in technology and in society, and you are able to appreciate the various subjects that we have touched, right? And another thing to note here is that another thing which is very interesting about physics is that you can be a physicist anywhere, and as long as your work is meritorious, if it deserves merit, your work would be recognized. And that is true for all kinds of sciences. No matter what your background is, which country you are from, it does not really matter. So you can find great scientists. You must have heard about these names of these scientists already, some of them at least, and you can see that they come from all kinds of countries, they come from all kinds of backgrounds, and they come from all kinds of fields as well. So with this, I hope you have developed some appreciation for physics, and you will now aim to become a very good physicist.